So now I want to talk a little bit about image formation by lenses and mirrors. So, in the previous segment, we saw that our brains can be tricked, even by just a flat, plain piece of glass or a flat-sided aquarium. Our brains can be tricked into thinking that something is in a different location than where it actually is. Like my face is right here, but I can make you think it's in a different location with this magnifying glass, right? It appears that my eye is in a different location than where it actually is. The image of my eye is not in the same place as my actual eye is. That's what we're going to be talking about here. And in order to wrap our brain around that, we're going to have two kind of different ways of looking at it. And the first is a graphical way where we're going to draw pictures, and we're going to use pictures in order to figure out where the image will appear from a lens or a mirror. And then after that, we're going to get an equation, so we're going to be able to do some calculations and reach the same conclusions. So let's start with lenses. Here we see a couple of lenses. This is called a converging lens. This is called a diverging lens. This is called a converging lens because the light rays converge or they come together to a point right here. This is called a diverging lens because the light rays spread out. It causes light to spread out, hence the name diverging. The shape of this lens we call a convex lens. When it's shaped like this, that is convex. When it's shaped like this, that is concave. So this is a concave lens. And a way to remember that is that this is kind of like a cave, right? This side right here is a little opening, kind of like a cave. So in this case, a concave lens is a diverging lens, and a convex lens is a converging lens. This length right here we call the focal length. So if we send in parallel rays, a very distant object is a nice source of parallel rays. We send in some parallel rays, they will converge right here. At that point where they converge, we define that as the focal point. If we send parallel rays into a lens, a diverging lens, they will diverge or spread out. They will appear to come from some point right here. That's what we call the focal point. So the focal point of a diverging lens is the point at which it appears to come from. The light appears to come from once it diverges, once a parallel set of rays diverge passing through the lens. So important sets of rays for a converging lens. And we're going to go through converging lenses, converging mirrors, diverging lenses, and diverging mirrors. And we'll see that the rays are all very similar. In order to wrap our brains around this, we're going to think about how do rays behave. Parallel rays, when they come into a lens, how do they behave? And how do rays behave that leave the lens parallel? And then we're going to have one ray that goes right through the middle, or any ray that goes right through the middle will be undeflected. So let's look here. We already showed this picture actually. Parallel rays will come in, they will get converged, they will converge at a point right here. That point is called the focal point. Now, it's important to recognize the symmetry here, right? If these rays were run in reverse, in other words, if we just turned those arrows around, they would follow the exact same path. In fact, that's what we've done here. This is the mirror image of this situation here. And so any light emerging from the focal point will come out of the lens parallel to the optical axis. The optical axis is the name we give for this line that goes right through the center of the lens, perpendicular to the lens. So any ray entering the lens parallel to the optical axis will get bent so that it passes through the focal point. Any ray coming from this focal point will get bent so that it emerges parallel to the optical axis. Any ray that goes straight through the center will not be bent at all. And so we're going to use, these are our important sets of rays that we're going to use to help us draw a picture to figure out where images are formed when we're using an image-forming lens or mirror. It's important to remember, here's our object. It's important to remember that there are an infinite number of rays that are going off in all directions from this object. Of those infinite number of rays that are going off in all directions from this object, we've chosen to represent 7 rays here, just to see what will happen. So these rays go through here and they get bent. Notice they always get bent towards the optical axis. So a ray coming in up here will get bent towards the optical axis. But a ray going down like this will get bent up towards the optical axis. It is a converging lens. Of these rays, 3 are our important rays. One ray comes in parallel to the optical axis, and it leaves the lens and heads through the far focal point. One ray goes through the middle and is not bent at all, and one ray leaves parallel to the optical axis. That means it must have come from the near focal point. A bit more terminology, and we'll come back to this near the end of this segment. The focal points are again identified here. Every lens has 2 focal points. Every lens has a focal point on each side of the lens. You'll find that a mirror only has 1 focal point. So we've got focal points on both sides of this lens. We identify that with an F. We use S to represent the distance from the center of the lens to the object, and we use S prime to represent the distance from the center of the lens to the image. This is the same notation we had when we did image formation by a flat surface. We can calculate the magnification, and we'll see that the magnification is simply the negative of S prime over S. There are some sign conventions to reckon with here. In this case, S prime is positive because it's on the right side of the lens, and S is also positive because it's on the left side of the lens. It turns out the sign conventions for S and S prime are slightly different. I do have a slide that lists all of the sign conventions in an organized fashion. We'll get to that towards the end of the lecture. We can also calculate the magnification, and the magnification is simply a ratio of the heights. So a magnification of 1 would say that the object and the image were the same height. A magnification of 2, for example, would mean my image was twice as large as my object. Okay, so this is a nice, pretty version of this. And notice it helps us to understand that our brains will be tricked into thinking there is an upside-down Christmas tree right here instead of an upright Christmas tree right here. That's what our brains are going to be tricked, right? So if I was over here looking at this situation, looking at this tree through the lens, I would not see the tree over here. Instead, I would see an upside-down tree right here. We know there's not actually an upside-down tree right here, but my brain is fooled into thinking there is. That's why we call it an image instead of the object. So here are a list of steps for using a picture to identify the location of an image. You're going to need to draw the optical axis. Again, that is this line right here that goes perpendicular to the lens through the center of the lens. This is your optical axis. Center the lens on the axis. We're going to mark and label the focal points. Represent the object with an arrow. In this case, we've drawn a pretty tree. An arrow is generally easiest. And it says it's best to place the base of the arrow on the axis. We'll do that. So you place the base of the arrow on the axis and draw the arrow about half the radius of the lens. That's something that you just kind of get better with practice, kind of seeing how these things will scale. Then we draw the 3 special rays. Okay, so these are the 3 special rays I was talking about just a second ago. One ray comes in parallel to the axis. One ray goes out parallel to the axis, and the other goes through the center and doesn't bend. Okay, we're going to see that we have a list of steps for all 4 scenarios. Diverging lenses, converging lenses, diverging mirrors, converging mirrors. But I think if we can kind of see this pattern, it'll help us wrap our brains around it, right? Our 3 rays are slightly different for all of those situations, but they are all similar in that we have one that enters the lens parallel, one that leaves parallel, emerges parallel, and one that goes through the center and does not bend. Now, we're going to find the place where the rays converge. That is the location of my image. Now we can measure distances we need or measure heights to calculate magnifications and answer whatever questions are asked. Okay, that's the basic idea here. Let's do a couple examples. Okay, so here we have an object 30 centimeters in front of a converging lens with a focal length of 10 centimeters. Use ray tracing to determine the location of the image, and then is it upright, inverted, real, or virtual? Okay, well, for starters, what we want to do is we should identify our optical axis. Okay, so here's our optical axis somewhere in here, and we'll just make a quick line here. There's our optical axis. Now let's draw our lens.
somewhere in the middle here. Something like that. Now we need to identify a scale. Let's go ahead and let 1 square equal 2 centimeters. Now we should mark our focal points. And it says we have a focal length of 5 centimeters. So 5 centimeters is represented by, 10 centimeters. It says our focal length is 10 centimeters. 10 centimeters would be 5 squares. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, now let's draw our object. Our object is 30 centimeters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right there will be our object. And we'll go ahead and make it 4 squares tall. Arbitrarily, right? They didn't tell us how tall our object was. So we'll just pick 4. Okay, so what are our rules? 1 ray comes in parallel, or 3 important rays. 1 ray comes in parallel and emerges passing through the far focal point. Something like this. Notice that the refraction, I've drawn the lens with some thickness to help me sort of visualize it. But any of the refraction happens right here along the line. And that is the plane of the lens. And so this is the thin lens approximation. So 1 ray went in parallel, 1 ray leaves parallel. If it's going to leave parallel, then it has to make it through this near side focal point. Like this. And then emerges parallel to the optical axis. The third important ray passes through the center of the lens undeflected, like this. Yeah, there we go. That's our ray tracing. Now we see that our object is right here. And what can we conclude? It is inverted. Is it real or virtual? Well, the light rays actually diverge from this point right here. They actually do. So my eyeball is over here, and I'm viewing this, right? I'm viewing this object through this lens. If I'm viewing this object, I don't actually see the object right here. I see it right here. So I call that the image. Now, since the light actually comes from this spot where my brain is tricked into thinking the object is, since the light actually does come from there, it is a real image. And we will see that in single lens and single mirror systems, inverted images are always real, and real images are always inverted. Okay, so this one's a little bit trickier because in this one we have a situation where our object is in between the lens and the focal point, and so we end up with virtual images. So there's our optical axis, and for this one, we'll use a 1 centimeter equals 1 square scale. And so here we'll something like that. Mark our focal points, focal length of 10. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. Great. And then our object is 6 centimeters. 1, 2, 3, 4, 5. And we'll go ahead and make there's my object. Great. So 1 ray goes in parallel to the optical axis. Well, if it's going to do that, it's going to get bent towards the optical axis because it's a converging lens, and it will go through the far focal point. Ray 2 emerges parallel to the optical axis. Well, if it's going to emerge parallel to the optical axis, that means that it must look like it came from this focal point. Something like this. So now it's not actually coming from there, it's coming from here, but it appears to come from there. And remember, of the infinite number of rays that are coming off of this object in all directions, we're picking these three because it helps us wrap our brains around the images that are formed. The third of these important rays goes through the middle undeflected. Well, I promised you a virtual image, and indeed these rays do not converge. This is definitely virtual. In order to figure out where our where our image is formed then, we will need to trace these backwards to see where they appear to come from. And it appears that they have met together right here. There is my object. So if we were to identify, that's S, that is S prime. So we have upright and a virtual image. And you can see that it is greatly magnified, right? So if my eyeball's over here and I'm viewing this object through this lens, I won't see it right here, right? My brain will be tricked into thinking it's right here. Of course it isn't.
Okay, so here's a nice version of what I just drew. We see that sometimes if our object is inside of the focal point, then we end up with an upright, larger image here instead of the inverted image. And you know, the thing is that the rays don't converge over here, so we have to dash them back, as I did in the example. This is just a little bit nicer drawing. Now for diverging lenses, it's a similar situation. We still have our three sets of rays. It's a little bit trickier, I think, with a diverging lens, because we have to think about where the rays appear to come from. A parallel ray that comes in parallel to the optical axis will get bent in a diverging lens such that it appears to come from this focal point right here. Similarly, a ray that is heading towards the far focal point will get bent and emerge parallel. And of course, any ray going right through the center will not be bent at all. A set of steps for a diverging lens looks like this. Steps 1 through 3 is exactly the same. Now we're going to draw our special rays. One ray hits the lens, it's traveling parallel to the axis, and then it goes to the lens. One ray heads towards the far focal point and emerges parallel to the axis, and one ray goes through the center. And again, we're going to have to trace the rays backwards. Here we are going to deal with virtual images, right? So diverging lenses always produce virtual images. So in this case, we're always going to have to do that little dash, dash, dash our lines back to see where they appear to converge, because they won't actually converge at any point.
So there's our optical axis. Let's draw our lens in here somewhere. And again, we're going to have all of the refraction happen right along this line here. And so we've just sort of included this drawing of the lens to help us visualize the situation. Let's pick a scale. Again, let's use 2 centimeters equals 1 square. So we have a focal length of 10 centimeters. 1, 2, 3, 4, 5. Again, lenses have focal points on both sides. 1, 2, 3, 4, 5. And we have an object 20 centimeters away. 1, 2, 3. Again, we'll just make something like that. There's our object. Okay, so one ray heads in parallel. Now, when it gets to the diverging lens, this ray is going to get bent away from the optical axis, away from the optical axis. So it's going to have to go out here somewhere. Well, it's going to appear as if it came from this focal point right here. One ray emerges parallel. Well, if it's going to emerge parallel, it's got to look like it's heading towards this far focal point. And then it emerges parallel to the optical axis. One ray goes through the center, undeflected. Like that. Now we see here we are definitely looking at a virtual image because these rays do not actually intersect anywhere. We're going to have to do a little dashing them back to see where they appear to come from. And we see that they do appear to come from right here. There is our image. So it is upright and it is virtual because the light does not actually come from this point. My brain is over here. It is fooled into thinking that there's something here. There really isn't any light being emitted from that location.